For the last few classes, we are discussing about classification of variables based on scope and lifetime. And so far, we have seen automatic variables, global variables, and static variables. And today, we are going to see one more class of variables called register variables, and after that we shall also discuss about bitwise operators, which perform operation at the bit level or binary digit level. So that is what we are going to do today. So the topic is register variables and bitwise operators. First, we can see what are register variables, and before we look at an example program using register variables, let us see how a program statement is getting executed in the central processing unit of a computer. So we are going to see how computation or execution of an instruction is happening in a central processing unit. So this is a figure which I copied from the internet, from this web page. Here what I am trying to explain is how an instruction or a statement in a C program will finally get executed. So consider an example where a statement B gets the value of A plus C, which is a statement in C program and which needs to be executed by the central processing unit, and assume that now the values of A, B and C are available in the CPU registers R0, R1 and R2. And in the next semester, you will be learning about the basic computer architecture, maybe in computer organization and architecture, and you will also learn about the digital circuits in it in another subject, maybe logic system design or switching theory, whatever. And we don't have to go for the details about that, but I will give you the basic information for you to understand how a program statement like this is getting executed. And now assume that the value of A is available in the register R0 and the value of C is available in the register R2, and you have to find the sum of A and C and then assign it to B. Suppose that B is now represented by the register R1. So basically what the arithmetic and logic unit needs to perform is take the input from R0 and R2, which is 5 and 9, perform addition in the arithmetic logic unit. So you will get 14, and then you copy the result and put it in the register R1. Okay, that's what the CPU can do. If R0, R1 and R2 respectively store the values of A, B and C. And so here how basically this happens, and the programming language statement will be translated into binary, and then it is what is called a binary instruction, and the binary instruction during the execution is actually stored in the computer memory called random access memory. And here you assume that this particular statement is converted into binary, and that binary instruction is available at the memory address 44. And so far in this course, whenever we discussed about memory addresses, we were looking at these addresses in the RAM, in the memory. And okay, suppose this instruction corresponding to this, there is a binary instruction which is stored at address 44. Then how the CPU knows where is it stored? It is actually remembering it in a register in the CPU which is called a program counter register, PC, which stores the address of the next instruction to be executed, which is 44. That means the next instruction needs to be taken from the memory. So what will happen is the PC will give the address will be given to the memory unit through the address bus. It is the address bus to carry the address. So the address is reaching into the memory unit, then that particular memory unit will be accessed, and the data in that, now the instruction corresponding to this will be transferred along this data bus and is reaching into the central processing unit. Okay, and once an instruction reaches here, it is getting stored in the instruction register IR, and the instruction register is interpreted by the processor, and accordingly it will generate control signals to control the operations in the arithmetic logic unit. So what is the control required? The control says that okay, now the order should function is the control given, and it will also tell that you should add the content of R0 and R2. Assume that the processor supports it. Okay, that is the control. How is it performed? The instruction is taken from the address given by the PC through the bus, and it is getting stored into the instruction register. Then it is interpreted, control is generated. The moment the control signals are generated, the corresponding circuit in the arithmetic logic unit will be triggered or may be requested to perform the action. The action will be performed only on the registers in the microprocessor. So here this is how it is being performed, and we had this assumption that the values are already available in the registers, but basically you know that all your variables are getting memory allocated here. Okay, so before performing the execution of an instruction, the system should first copy the values of the variables from the registers into the from the memory into the microprocessor or CPU registers. Okay, only after that it can perform its operation. So basically, for discussing the first topic today, we have discussed about some basic operations that we need in the computer hardware. So the data that the program is going to act on must be available in the CPU registers for enabling the arithmetic logic unit to perform the required operation. And if you want to perform addition of two variables, say A and C, first the values of A and C which are available in the computer memory, which is RAM, must be copied or fetched into microprocessor or CPU registers. So this is a time consuming operation when compared to the execution of the ALU. So the data needs to be fetched or copied from the main memory of the computer, which is RAM, into the microprocessor register. Now you assume that suppose C programming language allows you to directly store the variable or allocate CPU registers for the variables, then the fetching of data from memory into register is not required, and thus the execution becomes faster. And now we are going to see a class of variables which may be allocated microprocessor registers to store their values rather than main memory. And that is the first topic that we are going to learn today. So we are moving on to that topic, register variables. Let us try to understand how can you do it with an example. So here is an example where you are declaring three integer variables a, b and c as register variables. Okay. Then what are register variables is what we are going to learn. The storage class register represents the request that CPU registers may be allocated to the variables if possible. So we are requesting by this storage class specifier to the system or computer to provide us microprocessor or CPU registers for storing the values of a, b and c. That's it. And if the values are stored in registers directly, then execution becomes fast because already the values are available in the CPU registers. Just perform the action without waiting for data copying from memory. And one point that you have to note is that when you are having registers allocated for the variables, then address operator is not allowed, because the address operator works on memory only. That is, if the variable is getting memory allocated in the RAM, then the address operator is valid. And the system will allocate memory based on the availability of registers. If registers are available at that point of time during the execution of this program, then registers may be allocated. Otherwise, it will only allocate main memory. And if registers are not allocated, then variables will be treated as automatic variables. It's very important. That means if you are not getting registers free during the execution, then they all will get memory allocated in the RAM or random access memory, which is the main memory of the computer, and in that case all these variables will be treated as automatic variables. And the last point about register variables is scope and lifetime of register variables, which are same as that of automatic variables. So the only difference is that here, if possible, CPU registers will be allocated for the variables, otherwise they are same as that of automatic variables. So with this, we are now proceeding to the next part of this lecture, where we are going to learn about bitwise operators. So what are bitwise operators? They are operators acting on your data at the binary bit level. You know that a single data item is represented by a sequence of binary bits. For example, if you are assuming that the memory requirement for an integer is 2 bytes, then 16 bits are there representing an integer value, or it could be 32 also. And bitwise means if you perform an operation, then the operation will happen at the level of bits. In the computer organization and architecture, you will learn more about the computer hardware, and in another course which is logic system design in your third semester, you will learn about how the registers are designed and implemented, where you can see that in the register each bit of the register, maybe 8 bit or 16 bit or 32 bit or even 64 bits, each bit is represented by a hardware circuit, which is basically what is called a flip-flop. You don't have to worry about all these things. You just assume that there is a hardware circuit which can hold a single bit, and a register is nothing but a sequence of that such hardware circuits, and from each register you can access the individual bits. Okay, with this let us proceed and see what are bitwise operators. We will first look at bitwise complement, and I will try to explain to you what are bitwise operators using examples. So here is a program that just two statements where I am assigning a hexadecimal value to a short integer variable, and then I am applying the unary bitwise operator complement, which is just the tilde character. That means you just print the complement of A, and if you execute you will get this output. Complement of A is the hexadecimal value is printed, and you don't have to worry about how is it computed, that I am going to explain. So this is what you are trying to perform. The complement of, this is the prefix required for a hexadecimal value, the complement of this hexadecimal value. Now to understand how is it performed, let us expand this hexadecimal value. You know that each hexadecimal digit is represented using 4 binary digits. So this is how it is represented. 8 is represented as 1000. This is binary equivalent of 8. 0 by 4 zeros, and F is the last hexadecimal value, which is by 4 ones. I hope you already know this, otherwise just take it from me. Each hexadecimal digit is represented by 4 binary digits. You can just convert it into value and see that it is correct. Now what you have to do, you have to complement it. Complement means each binary bit needs to be flipped, 1 to 0 and 0 to 1. If you do that, you will get it. It's very easy. 1 to 0 and 0 to 1 is what we did. And if you look at the hexadecimal equivalent, this is the value. This is 7, all these are F and 0. And this is exactly what we are getting printed here. Okay, I hope you got it. So the only difference here is that the operation is performed at the bit level. Each bit is separately accessed and complemented. That's it. And you may find application for it. Suppose that you have a binary sequence and you just want to complement it, just go for it. The next operator that we are going to see is bitwise OR. We want to perform the OR operator. The OR means if you perform OR between two binary bits, if both are 0, then the answer is 0, otherwise it is 1. That is 1 or 0 is 1, 0 or 1 is 1, 1 or 1 is 1, and 0 or 0, that is the only case when the operator results in 0. See here again, consider an example. I am having a hexadecimal value in A, another value in B. I am performing the OR between this hexadecimal value. So the pipe character is the OR operator, single pipe. Not that the double pipe is actually the logical OR. Here is a single pipe character which is bitwise OR. And if you do it, you are getting this result. How? So these are the two values on which we want to perform the binary bitwise operator OR. So expand it. So this is how you expand. This is the equivalent of this hexadecimal value, and this is the equivalent of this hexadecimal value, which if you want you can verify offline. And we want to perform OR. OR means perform the OR operator at the level of bits. This is 1 or 1 is 1, and you will get 0 only if both the bits are zeros, and we don't have a case like that. Everywhere at least one bit is 1. So this is the result, and if you look at the hexadecimal value, all these are F, and hence we are getting that value printed out. Maybe you can try to find an application for the bitwise OR. And suppose that you are programming for an embedded system, maybe for a device in the computer network. That device is receiving a sequence of bits from the network, and suppose you want to set, say you are receiving 30 bits, and suppose that you want to make all the middle 10 bits 1. That is what you want to perform. For some requirement of your system, 30 bits are received, 1 to 10, 11 to 20, and 20 to 30. And suppose you have to set a part of it, say from 11 to 20, you want to make all the bits 1 regardless of what is already received. Then what do? You form a binary string of length 30, where the first 10 bits are zeros, then the second 10 bits are ones, the last 10 bits are zeros. Then you just perform OR with the original 30 bit data. So what you will get is the first 10 bits of the original data will be retained as such, then the second 10 bits will be set as 1 regardless of what bits are received in the original message, and the last 10 bits also will be retained. You can think about it offline. This is an application. You can try to find more applications. Think about it and come up with more applications for the bitwise OR. And with this, we are now proceeding to bitwise AND. I think now the context is very clear. So let me proceed. So I have two hexadecimal values in A and B. I am performing bitwise AND, which is a single ampersand symbol. Recall that double ampersand means the logical AND, which is performed on the entire data. Here it is bitwise AND. And if you perform, you are getting this result. How? These are the values, expand it, these are the expansions, and AND means it will give you a 1 here if both the bits are 1s. And if you look at the result, all these are 0 because at least one bit is 0 there. And here it is 1 because all bits here are 1. And that is what you are getting. Please verify it offline. This is the result that we are getting. And if you look at the hexadecimal equivalent, this is the value which is what is getting printed. And this is the AND operator. And maybe we can find an application. Again, consider the embedded system where you are programming for a network switch and you received maybe 30 bits from 1 to 30, and suppose in this case you want to say make the middle 10 bits 0. So what do? You form a 30 bit binary string where the first 10 bits are 1, the second 10 bits are 0, and the third 10 bits, the third part is completely ones. So ones, zeros, ones for our purpose. The middle bits needs to be reset to 0. You just perform the AND operation, then you can see that the first 10 bits are preserved, second 10 bits are reset to 0 whatever it is, and the third 10 bits are again preserved. This is just an application, and you can find think about it and find more applications for the bitwise AND. Now let me proceed to the next bitwise operator, which is exclusive OR. So what is exclusive OR? Now I will try to explain with example. Okay, these are the two values I want to perform exclusive OR, which is this caret symbol. Okay, you can find it on your keyboard on the top above some numbers. Okay, you do that, and if you do it, this is the data getting printed. And how is it done? These are the two values on which we have to perform the operation. Expand it, you can verify the expansion, and exclusive OR means if you perform it at the bit level, if both the bits are same, then the value will be 1. 0 exclusive OR 0 is 1. Similarly, 1 exclusive OR 1 is 1. That is, if both the bits are same, 0 or 1, then the result is 1. Otherwise, that means if one bit is 0 and the other bit is 1, then the result is 1. Okay, that's it. If both the bits are same, then 0. If the bits are different, like 1 0 or 0 1, then it is 1. So that is the semantics of the exclusive OR operator. It's a very useful one, and this is the result that we obtain. And if you convert to hexadecimal, like printing using %x, this is the value which is what we are getting. Sorry for the typo, this should be F. Okay, sorry for that. We verify that it is F. So this is what is getting printed. And if you want to see an application, consider the same scenario. You are programming for a network switch. You received a 30-bit binary message, and now suppose you want to complement a part of it. If you want to complement the entire sequence, just go for the unary complement operator that we discussed as the first binary operator. But suppose you want to complement only the middle 10 bits, what you can do is you can set a 30-bit sequence where the first 10 bits are zeros, second 10 bits are ones, and the last 10 bits are again zeros. And you perform this operation, you can see that the first 10 bits of the original message are preserved, the second 10 bits are complemented, and the third 10 bits are again preserved. And why is it complemented? Because you are performing exclusive OR with a 1. Every bit you are performing this. Suppose originally it was a 1. So 1 exclusive OR 1 gives you 0. And suppose originally the bit was 0. And 0 exclusive OR 1 will give you 1. So you are just complementing it. I hope you are getting me. Otherwise, please watch it again and see that it's correct. And you can find more applications for exclusive OR. With this, let us proceed to the next bitwise operator, which is right-shift. Look at an example. I have a single value which is hexadecimal, and I am going to right-shift this by 2 positions. To 2 positions, right-shift. It's a binary operator because the number of shiftings required is to be specified as the second argument. And if you perform, you will get this is the operator 2 greater than simples is for right shift. This is the value that you are getting. How? So this is what you want to perform. Expand it. This is the hexadecimal value converted into binary. So you want to right shift this 2 positions to the right. So you want to right shift. This is the equivalent hexadecimal. You want to do right shifting. So what will happen? The last 2 digits will go out. Okay, this will go out. That is right shifting. These 2 ones will come here. Now the question is, you want to fill two positions here as a consequential impact because you have performed a right shift for two positions. Now the question is, so what bits values will come here? It could be 0 or 1 or maybe arbitrary binary values, but the C semantics is that it provides 0 there. Okay, two zeros will be inserted here and it's just like you are pushing it to the other side two positions. So these two bits will go out and two zeros will come here. And this is what you are obtaining. You please verify it offline. I am just performing two right shifting to two positions, and if you look at the hexadecimal equivalent, these are the values, and so this is what we are getting, and that is what you are getting printed. And now maybe you are interested now in knowing about an application. This is a very useful and powerful operator. This can be used to perform division. You can easily verify that if you right shift to one position, then you are actually dividing the original value by 2. You please verify it. So very powerful operation, because the division, if you perform with a direct hardware circuit, it is very costly. You will learn it in your logic system design course. But if you perform a single binary right shift for one position, you will finish it in a single clock cycle and you are performing division by 2. Okay. Now let us proceed and look at the last operator that we are going to learn today from the bitwise operators, which is left shift. This is just the opposite. I hope you know what it is. So this is the operator, two less than signs. So I am going to left shift this value two position to the left and you will get this value printed. How is it getting printed? This is the operation. You expand, you verify the expansion, this is correct, and you want to perform left shift. So what will happen? The leftmost two bits will go out, okay, and 2 will come here, and 2 zeros is coming there, and if you look at, you are getting this value, and if you want to look at the hexadecimal, this is the hexadecimal value and that is what is getting printed. So this is bitwise left shift. This is again very powerful, just opposite to the right shift. When you left shift by inserting a 0 to the right, you are performing a multiplication by 2, and this is a very important operation and it is a very common operation in cryptographic algorithms. Cryptographic means, suppose you want to protect your data from unauthorized access. When you are transferring your data through internet, you can actually transform your data to a form which a third person cannot understand what it is, and it is performed using what is called cryptographic algorithms. And in cryptographic algorithms, they are performing multiplications with prime numbers and all, and it is very costly, and it is very common to use left shift a number of times to perform squaring or by repeated multiplication with 2. Okay, this is just for motivating you. And today we have seen register variables. They are having the same scope and lifetime as that of automatic variables, but here the only difference is that if CPU registers are available, then your variables will be getting CPU registers to hold their values. Then the execution becomes faster because data is then available in the CPU registers itself. Otherwise, you wanted to copy it from the main memory to the register. So that's what we learned about register variables, and after that we have seen bitwise operators. Suppose all your data is copied into microprocessor registers or CPU registers, then you can perform operations at the bit level. We have looked at unary operator complement, then the binary operators OR, and exclusive OR, then two more binary operators for left shifting and right shifting. Thank you.